Hello ladies and gentlemen, let's get this going I guess. So we are talking about air-water interactions, and in that context I guess we were talking about dissolution of different environmentally relevant gases, and the primary gas that we are concerned with here is carbon dioxide obviously. Again, carbon dioxide, once it dissolves into the water, you will have carbonic acid being formed. So you are going to have acid base reactions, right? And you are going to what do we say, vary or lead to change in the master variable, which is pH. pH affects human life, right? You are going to have a specific pH for the gut, you are going to have a specific pH for your blood, and so on and so forth. Similarly, aquatic life also depend upon pH, and also you are going to have different minerals or metals being relatively more mobile or immobile based on the pH, right? That is why we call that as master variable. In that context, we obviously need to understand how or what is going to happen when an acid releases a proton, or we need to understand when is the acid going to release a proton, let us say, right. In that context, I believe we were looking at this particular acid dissociation constant pKa, right, pKa equal to minus log K1 for this particular carbonic acid being dissociating into H plus and HCO3 minus, we have that to be 6.3, right. And let us just look at some of the SDT constants, right, our acid dissociation constants. Let us look at pKa out here, right, obviously because you have what do we say, different orders of magnitude. So, it is easier to understand it when we look at the or take the logarithm of Ka. So, we are going to look at pK out here. So, first is HCl. Typically you know that HCl is a strong acid. So, why is that? You see that the pK is pretty low. Again, what does it practically mean when we say pK is low? We will look at that I believe in the next slide. I think I do have the relevant graphic that I wanted to share with you. Again, H2SO4 going to H plus and HSO4 minus, or sulfuric acid dissociation. Again, very strong what do we say now or very low pK, that means very strong acid. Again, what does this mean now? We see that HCl can dissociate into H plus and Cl minus. When I say that Ka is equal to 10 power 3, and what is K? Equilibrium constant, and equilibrium constant is nothing but here H plus and Cl minus, the products, right, H plus by HCl, right. So, what does this mean? Obviously, it means that the products are what do we say, going to be at a remarkably high concentration compared to the reactants, which is HCl. So, meaning that HCl will almost always try to what do we say, release the proton H plus, let us say, right, or it is going to deprotonate. Why is that? Because you see that Ka is pretty high, or it is 1000 I guess, right, and similarly with H2SO4, that is what you see out here. And for nitric acid too, I guess it is still considered to be a strong acid, and again thus two I guess, even yes. So, strong acids I guess we can say when the pK is up to around 2.1. So, here we end up with start looking at phosphoric acid. Again, this is a triprotic acid, right, the 3 protons, triprotic, H3PO4, H2PO4 and HPO4 2 minus, right. And where is your carbonic acid? H2CO3 and HCO3 minus. And typically we pay great attention to H2CO3 and HCO3 minus because calcium carbonate, the most widely available what do we say, mineral out there, and also carbon dioxide. So, the carbonate system plays a remarkable role in sustaining what do we say, life on earth indirectly. Why do I say that? Because let us say, as you see it has a pKa that is almost near to the neutral pH of 7, let us say, almost here, right. So, it acts as a good buffer, let us say. Without a good buffer, you are obviously going to have drastic changes in pH whenever there is any external what do we say, influence with respect to H plus being given out or taken out, right, or given or taken out. So, that is why I guess H2CO3 plays a considerable role. So, again as I mentioned, what does it mean when we say pKa, let us say, yes, we see that is pretty obvious. HCl and H2SO4, they want to donate their H plus pretty much. But when we look at these acids I guess and their conjugate bases, what do we need to understand? Let us say we need to look at the speciation. as in we need to understand, let us say with respect to H2CO3 and the conjugate base HCO3 minus, when will the proton be released, let us say, or if I add carbonic acid to a particular system at a particular pH, how will the system behave, and so on and so forth. So, let us look at that in detail, as in what species are going to be formed. So, here we have speciation with pH, and here we have the what do we say, pH pKa graph. So, on the x axis you have the pH, and here you have the relative concentration of the 3 species. That is why we call it speciation. We have H2CO3, HCO3 minus and CO3 2 minus here. So, this is H2CO3 and HCO3 minus, and this is CO3 2 minus. And then you have, as we saw, what is the pKa out here, that is 6.3 and 10.3 as we discussed earlier. So, 6.3 that is out here, and or here I guess 6.3 or 6.4 according to this graph, and 10.3 I guess, right. So, what does this really mean, let us see, for example, you have Ka is equal to what now, H plus HCO3 minus HCO3 minus by H2 CO3, let us say, right. And you have the Henderson-Hasselbalch equation. I think it is pH is equal to, or when you take the logarithm of this particular equation and play around, you will end up with this. Well, why not take a shot at it? Take the logarithm here, log of Ka is equal to log of H plus log the acid, not acid, the conjugate base by the acid, I guess, right. So, if I want to have pH and so on and so forth, I am going to take this term out here and this term out here. So, what do I end up with? Minus log H plus, which is nothing but pH, and minus log Ka on the right hand side, which is nothing but pKa, plus log of the conjugate base or HCO3 minus in this context by H2CO3 or the protonated form, right. So, when I have the pH is equal to pKa, when the pH is equal to pKa 6.3, right, pH is equal to pKa. So, they both of them cancel out. So, what do you then end up with? You see that the concentration of the conjugate base and the relevant acid are going to be the same when pH is equal to pKa, right. So, that is what you see out here. When pH is equal to 6.4 or 6.3, you see that the concentration of H2CO3, right, and concentration of HCO3 minus are the same. Similarly, when the pH is equal to pKa2, which is 10.3, right, what do you see? You see that the concentration of HCO3 minus and concentration of CO3 2 minus are the same, right. So, again that is the reason I mentioned earlier again that it acts as a good buffer near around pH 7. So, again what does this tell me that? What does it tell me now? When the pH, let us say here we have pH is equal to pKa plus log A minus by HA, deprotonated by protonated form, let us say. When the pH, let us say, is less than the pKa by 1, what does that mean? So, if I have what is this now, 6.4 is my pKa, and if the pH is 5.4. So, pH minus pKa will then be minus 1 is equal to log of this particular set of terms. So, what will I have? I will have A minus by HA is equal to 10 to the power of minus 1 or 1 by 10, or you see that HA is going to be 10 times the concentration of A minus. So, what do you see? At 5.4, you see that most of the the carbonate species will be present as H2CO3 as 5.4, right. So, similarly, if I work it out for 7.4, most of it will then be present as HCO3 minus, right. So, you see that there is a very narrow range, I guess, within which it can act as a good buffer, And more importantly, now you can see that if the pH is 5.4 and you add carbonic acid to the system, it does not really dissociate much because most of it is present as H2CO3, that is what we saw out here. So, very little will dissociate into HCO3 minus, so the pH will not really change, right. So, that is something to keep in mind. So, what do you see as we approach the pKa? The concentration of the acid starts decreasing rapidly, and then I guess it reaches almost 0, and then the deprotonated form, it is going to start increasing. What do we see out here? The H2CO3 decreases as we reach and move on from the pKa, and then obviously again simultaneously the HCO3 minus keeps increasing now, right. And then as we keep increasing the pH, what do we see? HCO3 minus starts decreasing while CO3 2 minus starts increasing. So, you can understand and see, let us say at what or which pH the relevant species is going to predominate. So, for example, if pK is 10.3, you know that at 11.3, right, CO3 2 minus is going to predominate, and the pH range between let us say 7.3 to 9.3, HCO3 minus is going to predominate, and below 5.4 you know that H2CO3 is going to predominate. So, this will give you an idea about how the system will behave or which species let us say are going to be relatively predominant at which pH ranges. Again, what does that depend upon? It is obviously depend upon the pH of the solution and the pK of the relevant acid, right. So, again one other aspect or example, I guess here we have H3PO4, the phosphoric acid, triprotic, I guess, yes, and obviously we now have 3 acid dissociation constants, pKa1, pKa2 and pKa3 around 2.3, I think around 7.1 and I think around 12.2, right, but we can just check that out here. So, 2.1 and 7.2 and 12.3, we were close enough, right. So, we have that, and what do you see now? At pH 2.3, H3PO4 and H2PO4 are going to be at the same concentration, and you see that below pH 1.3, right, 2.3 minus 1, most of it is going to stay as H3PO4. Again, as we keep approaching the pKa, it is going to start decreasing, and as we move further from the pKa, H3PO4 is going to be almost 0, and then you are going to have a simultaneous increase in H2PO4. Then as I keep increasing the pH, what is going to happen? H2PO4 keeps decreasing and HPO4 minus keeps increasing. So, near the neutral pH, what are you going to have? You are going to typically have H2PO4 and HPO4 minus, H2PO4 minus and HPO4 2 minus, right, and not typically H3PO4 and PO4 3 minus, right. So, this will give you an idea about which species will predominate at which particular what do we say pH, let us say, right. So, for example, if I know that phosphorus or phosphates are present and the system is at relatively neutral pH, I know that it is typically going to be H2PO4 minus and HPO4 2 minus, let us see, and it is going to lead to different what do we say effects on the equilibrium. We will look at that later, let us see, but that is something to keep in mind or learn, right. So, again we are back to carbon dioxide water interaction. So, what is going to happen to carbon dioxide that is in the gaseous phase? It is going to dissolve into water, right, aqueous phase. In aqueous phase, CO2 plus H2O, right, you are going to have, I guess, H2CO3, right, the carbonic acid, and that is what we have out here, carbon dioxide aqueous, more or less meaning H2CO3, right. As we know, H2CO3 can dissociate into H plus and HCO3 minus, and we know that HCO3 minus can further dissociate into H plus and CO3 2 minus, let us see. So, you are going to have this system in equilibrium, right, or if equilibrium is reached, you are going to have a fine balance between the phase change reactions and the acid base reactions, right. All these acid base and phase change reactions are going to play a role in deciding where the equilibrium is going to be and what the pH and such variables are going to be, right. Again, let me move on out here. So, in general we want to know, let us say the pH is at a certain level and you want to understand what is causing it, or let us say you want to understand, let us say given this carbon dioxide concentration, what is going to be the pH, let us say at a particular point in time or once the equilibrium has been reached, let us say. So, how are you going to solve for this? You are going to have to solve for chemical equilibria or equilibrium now. So, in this class we are not going to look at aqueous complexes, right, where metals and ligands form these relatively more stable aqueous complexes. We are going to look at some precipitation and dissolution reactions, right. Yes, we will not look at redox reactions though, but we will look at acid and base reactions a lot and phase change, I guess. So, in this class we are going to look at phase change, acid and base reactions and precipitation and dissolution. We are typically going to neglect aqueous complexes and redox reactions, obviously though that is not going to be the case. So, how are you going to solve for chemical equilibria? Depending on what you know, you have to list all the species that you think will be present at equilibrium. Let us say different cations and different anions, because I said we are going to neglect aqueous complexes and redox, you can limit your what do we say, number of species out here. So, first these are the unknowns, I guess, these are the unknowns, you are identifying the unknowns. Let us say again cations, anions and neutral species, these are your unknowns. Again, as I mentioned, acids and bases and some precipitation and dissolution reactions only. And again you can look at the equilibrium constant for this and see that it is pretty high, NaCl going to Na plus and Cl minus. You will see that equilibrium constant is remarkably high for this reaction. So, you can neglect salts, I guess, NaCl and such, again that is what we are saying. So, we have what do we say, for example 5 unknowns, and what do you need to solve them? You need to have 5 independent reactions. So, in this context obviously where will we get them from? We are going to get them from what do we say, understanding that the system that we are trying to analyze is at equilibrium. So, you are going to have the chemical equilibrium relationships. So, as I mentioned, we typically use acid base equilibria, and when we have carbon dioxide, let us say again in this example you are going to have 2 acid dissociation constants from this chemical equilibria, right. So, K1 and K2, this is not plus, obviously this is into here, right. So, you have these kinds of what do we say, reactions now, right. And then what else do you have other than chemical equilibria? You will also have, let us say, phase change. For example, if you are talking about carbon dioxide in open systems, you can have the Henry's constants or Henry's law giving a relationship between, let us say, the concentration in the aqueous phase and the partial pressure. So, that is one more independent equation, and depending on how the problem was defined, you will have, or you can, what do we say, come up with mass balance or component balance equation. As in, that if I am adding CO3 2 minus and there was no CO3 2 minus initially. So, irrespective of what the pH is, the CO3 total will be the sum of H2CO3, HCO3 minus and CO3 2 minus, let us say, right. Again, depends on how the question was defined, or depending on the amount of data that you have with respect to the species, that water has to form or is always electroneutral, or there has to be a charge balance, as in the sum of the equivalent concentrations of the cations is equal to the equivalent or the sum of the equivalent concentrations of the anions, right. So, these are the typical, what do we say, independent equations that you can get. Again, what are they? Chemical equilibria with respect to acid base, precipitation, dissolution and phase change, and mass balance or component balance, and with respect to electron neutrality. But in this class we are going to usually look at chemical equilibria, and rarely maybe will we ever look at electron neutrality. Why is that? Because for electron neutrality obviously you need to have a lot of what do we say, information about most of the ions out there. So, again as I mentioned, we will typically be looking at various chemical equilibria equations and then solve the equations, I guess. As we know, we need as many independent equations as we have the number of unknowns, I guess. And in general, depending on how we ask the question though, it is typically easier to first calculate H plus and then use it to calculate all the other species, let us say. For example, once you calculate the H plus, that you can calculate H2CO3, HCO3 minus and CO3 2 minus, right, because pH is equal to pKa plus log A minus by HA and so on and so forth, right. So, typically if you get the pH and the pKa, obviously you can get the other sets of information, I guess, piece of information. So, let us look at this example. So, I guess I am almost out of time. Let us just look at the question and then we will try to solve this, or we will solve this in the next class. So, here we have a question that asks us to calculate the pH of a water droplet, which we are assuming to be in equilibrium with the atmospheric carbon dioxide. Assume that there are no other species, keep that in mind, other than the carbonate species in the water, and assume that the carbon dioxide concentration in the atmosphere is 370 ppm by mole basis, I guess. Okay. So, mole basis. So, that is something to keep in mind. So, here what are our unknowns? Our unknowns are H plus and OH minus obviously, and H2CO3, and what else? HCO3 minus and CO3 2 minus, and we already have the partial pressure of carbon dioxide, let us see, right, and these are all the aqueous phase concentrations that we do not know. So, how do I or what do I need? I need 1, 2, 3, 4, 5 equations, I guess. So, I guess I am out of time. We will see how to solve this particular problem in the next class, and these are typical problems that we try to give you in the class, right, so that we keep you interested, right. Okay, with that I will end today's class, and thank you for patience once again.